Hi, my name is Emma Snyder, and this is Lab 4 of Circuits for Physics 2. The purpose of this lab is to observe the properties of circuits and how they are impacted by resistors and capacitors being placed within them. The fundamental principles of this lab are the energy conservation principles and currents conservation principles, which are shown below in these two equations. So basically, in this lab, everything kind of behaved the way it was meant to, and there were three parts to it. In part one, the total change in voltage around the circuit added together should be equal to zero and was equal to zero. In part two, the capacitor becomes charged and discharges at the same rate, but it varies proportionally depending on which resistor is in the circuit with the capacitor. And then the computed time necessary for the capacitor to charge was 60 seconds, which is what I computed using the equations. In this experiment one, this was the setup over here, and the system is the circuit, and then the surroundings are none, and then the voltmeter later on. And then the initial conditions are with the batteries disconnected, and then when they are connected, that is the final conditions. The circuit on the right was built, and the measurements on the ammeters were compared, which were both 0.02 amps, and then that didn't change when you turned it backwards. And then one was removed and replaced with a voltmeter, making the ammeters measurements fall to zero. And the voltmeter was measuring 3 volts, which came from the batteries. And then here is the table of data collected when traveling around the circle with the voltmeter. These sum up to zero because actually this is a -3 value at the top because this is a +3 value, and these add up to -3, so it sums to zero, as shown here on the diagram showing the voltage around the circle. And then this is experiment two. The circuit was the system, and then there were no surroundings. The initial conditions, the battery is not connected and no current is flowing. And then the final conditions, the battery is connected and the capacitor is charged. And the setup was using a 200 millifarad capacitor and a 10 or 20 ohm resistor in series with a 9-volt battery. And then we were measuring the amount of time it takes for the capacitor to fully charge, disconnecting the battery and closing the circuit, then measuring the amount of time it takes for the capacitor to fully discharge. And this was performed with both the 10 and the 20 ohm resistors. And the charging and discharging times for both resistors were equal, like the charge was equal to the discharge time, but they changed proportionally to the number of ohms in the resistor. The third and final experiment used the equation. This one was shown at the beginning, and then this right here is the equation when it's adjusted for this particular problem. The limit as delta V approaches zero when you multiply the RC over is 60 seconds. Excuse me. And then the initial conditions using the 200 millifarad capacitor again, the 9-volt battery, and this time a 30 ohm resistor. In this case, I believe it was a LiPo. And then the voltmeter measured it across like the capacitor, the voltage, and the battery was then disconnected, and then we discharged it. The final condition was that it reaches the maximum charge capacity, the current stops flowing, and the light bulb goes out. Because I used a computer program, there were no real differences between the calculated and experimental values that were found during this process. And this is true because it's an ideal system, as it is like nothing but the program, and it ignores everything that we have in real life. So basically, all the conditions are just at ideal points, and that's what the calculations also use. And there are likely only the sources of error if I made a mistake in constructing something or in misreading the any of the different things that were used to measure during that. If you did this lab in real life, the biggest difference would be that the actual ammeter would have some resistance to it, and therefore it would actually have a lower current running through it. So that's how it would change the reading based on if you use a simulated versus an actual ammeter. And then for the second what if question, the capacitor would be fully charged like immediately if there was no resistance in it. In the simulation, it would be 0 seconds. However, in real life, wires actually have some resistance to them. So the fact is that there would actually be some delay, though it may be minuscule and you may not actually be able to notice it. However, it would not be exactly 0 seconds the way it should be in the simulation.